Hello students, good time to all. I am Chandan Pradhan. Welcome to your channel Chandan Physics. In this video, we are going to discuss coherence as temporal coherence and spatial coherence. Let's begin. What is coherence? A wave which appears a pure sine wave for infinitely large period of time or an infinitely extended space is said to be perfectly coherent. If we consider a sine wave, like this, for infinite large period of time, then that wave is said to be perfectly coherent. But actually it does not exist. A light source is said to be perfectly coherent. What happened in case of light source? That light source, or we can say light waves, are pure sine waves for a limited period of time or limited space. As a result, we can say two types of coherence. As temporal coherence and spatial coherence. So, what is temporal coherence? Temporal coherence is also known as longitudinal coherence, and in case of temporal coherence, which is a measure of relation between phase of wave at different points along the direction of propagation of wave. Let me consider a light wave travelling along x direction. It is a light wave which is travelling along x direction. Here a point let A, here be a point let B let point. Let phi of A, that is the phase of that particular wave at point A, and phi of B is the phase of that particular wave at point B. Then the phase difference between these 2 points, here the phase difference, del phi is equal to phi of A minus phi of B. If that del phi is independent of time, then that particular wave is said to be the temporal coherence. If the phase difference is independent of time, then the wave is said to be temporal coherence. Example of a temporal coherence: Take example. In case of atomic spectra, it is helium light, sorry, for sodium light, sodium light source. In case of sodium light source, what happened? In that of atom, that is the ground state, that will be the excited state, this one is the ground state, that will be the excited state. So, when electrons are jump from excited state to ground state, they release some energy, that is the emissions. So, they emits light pulse. The excited atoms returns to the initial state, or we can say ground state. It emits the light pulse for a short duration. The duration may be 10 to the power minus 10 second in case of that sodium light, that is the sodium atom. Thus, the field remains sinusoidal for time interval of 10 to the power minus 10 second. In that of case, we take 10 to the power minus 10 second. At that time period, that wave is sinusoidal, after which the phase changes abruptly. Now, the field due to this light source, if we draw it in graph, the field due to that light source, here time period, and with the field. So, the graph looking like this. In some time period range, the wave looking like this. Another time period range looking like this. Then another time period or another bunch of atoms it is looking like this. So, the average time interval, here is a time interval, here also a time interval, this also a time interval, but we consider the average time interval for which the field remains sinusoidal. That means there will be a definite phase relationship exist, is called the coherence time. Now, we define the term as the average time interval for which the field remains sinusoidal is called coherence time. Coherence time tau. During the time, the distance travelled means the corresponding distance, the corresponding distance let L, for which the field is sinusoidal, the field is sinusoidal, is called coherence length, coherence length, and it is given by the coherence length L is equal to coherence time, the velocity of that propagation of wave at the velocity of light c. Here we can write that is the coherence length, the coherence time into velocity of light, that is the coherence time tau, then the coherence length L, and the coherence length is equal to coherence time into velocity of light tau, that is the average time, or we can say the coherence time, and the corresponding distance during that time period is known as the coherence length. Various relationship. The coherence time tau is of the order of reciprocal of frequency, range, that is del nu, that is coherence time tau is equal to 1 by del nu. Now putting that value here, therefore coherence length L is equal to tau c, put that value, that is c by del nu, that is another relation of coherence length, that is a relation, that is also another relation. Again from that expression, look here, that expression del nu is equal to 1 by tau. Since nu is equal to c by lambda, frequency is equal to c divided by wavelength. Now differentiating, we get del nu is equal to minus c by lambda square del lambda. That is the value of del nu. So that value is put here, which implies minus c by lambda square del lambda is equal to 1 by tau, which implies tau is equal to minus lambda square divided by c del lambda. Now we can put the value of tau in that particular expression. So we can get the coherent length. Therefore, coherence length L is equal to minus C lambda square divided by C del lambda, or L is equal to minus lambda square divided by del lambda. Now neglecting that negative sign, negative sign, we have L is equal to lambda square by del lambda. That is the another relation. Sorry, del lambda is equal to lambda square by del lambda. Look here. Now, when we neglect that negative sign, we take a form as del lambda is equal to lambda square by L. That del lambda is known as the line width. That del lambda is known as the line width. And we define another term. Lambda by del lambda is equal to Q, which is known as quality factor. Quality factor of each wave train. Quality factor of each wave train. These are a wave train. So, lambda by del lambda we define is the quality factor of each wave train, and del lambda is equal to lambda square by L, where del lambda is known as the line width. Now, the expression for coherence length will be how much? Therefore, L is equal to lambda into Q, wavelength into quality factor. These are the various ways to write the coherent length. Coherent length in terms of quality factor, coherent length in terms of frequency, coherent length as the product of coherent time, the velocity of light. These are some mathematical representation of coherence length. This is all about temporal coherence. Next, spatial coherence, another type of coherence. Spatial coherence, which is also known as transverse coherence or lateral coherence. What happened in that type of coherence? If a beam of light is said to be possesses spatial coherence if the phase difference of waves crossing the 2 points on a plane perpendicular to the direction of propagation of a wave is time independent. Let we consider two waves, one wave just like this along x direction, that is the direction of propagation of wave. Another wave also just same phase to that of previous one. There is no phase difference between the 2 points, or phase difference between them is 0. Then the 2 waves are the spatial coherence, therefore that is known as the transverse coherence. If we take that segment A, B, C, D, from that point P, that point Q, here let the phase be phi of P, here the phase be phi of Q. So, the phase difference del phi is equal to phi P minus phi Q. If that phase difference is independent of time, if del phi is independent of time, then the wave is said to be spatial coherence. That phase difference is independent of time, then that wave is said to be spatial coherence. Here we consider the beam of light travelling in x direction, and ABCD is a plane perpendicular to that of beam of light along x axis. We consider 2 points P and Q on this plane within that of beam of light. So, here the phase at point A, the phase at point Q. So, the phase difference, if that phase difference is independent of time, then we say that wave are said to be spatial coherence. We take examples of spatial coherence. How spatial coherence can easily explained in case of point source. For point source, let us consider light waves emitted from a point source S. Light wave emitted. Let A and B are 2 points laying on the line joining with that of point source S. So, the phase relationship between the point A and B depends upon that of distance AB and the temporal coherence of that of B. We know the temporal coherence or the coherent length is capital L. If look at the condition, if the length AB is very less than the coherent length, L is the coherent length, coherence length, then what happened? That length AB is very less than the coherence length. Then what happened here? There will exist a definite phase relationship between the points A and B. Again, if that length AB very greater than the coherence length L, there will be no coherence between A and B. Here coherence between A and B, here no coherence between A and B when that length is much greater than to that of coherence length. Now, if we consider a point C which is same, the distance of C is same as the distance of A from that of source. Hence, these 2 points A and C are said to be spatial coherence if SC is equal to SA, A and B are perfect spatial coherence, perfect spatial coherence at point A and C, at point A and C we get perfect spatial coherence. These 2 points have perfect spatial coherence. Now, for extended source, how we get that for point source? For extended source, we take Young's double slit experiment into our considerations. Let the source S and S dash separated by a distance L and S1 and S2 here S1, here S2, are 2 pinholes. These 2 are separated by a distance D. Now, the screen is placed now. The slits S1 and S2 are placed at a distance D from that of source. These 2 sources are independent, and these 2 sources produce their own interference pattern on that of screen. Here let we assume S1 is equal to S2 and S1O is equal to S2O. S1 same as S2, here is the point O. S1O is also same as S2O, where O is a point on that of screen. The distance between the source S and S dash small l, so S and S dash is equal to small l. The waves from S reaching at point O of that of screen through S1 and S2 have zero phase difference since the distances are same, and reaching at point O through S1 and S2, the intensity at O due to the source S dash depends on the path difference between S dash S2 and S dash S1. If the path difference that is S dash S2 minus S dash S is equal to lambda by 2, that path difference is equal to lambda by 2, then we will get a dark fringe at O. Then we will get a dark fringe at O. Here we get a dark fringe due to the source S dash, due to S dash. Here lambda is the wavelength of light, lambda be the wavelength of light. Look here, that is the minimum interference pattern produced by S dash will fall on the maximum interference pattern produced by S. Due to S, here we get the bright fringe, as there will be no such phase difference. So, we have the bright fringe due to S, but in case of S dash, here we get the dark fringe. Now, its maximum interference pattern is the bright one, its minimum interference pattern, that is the dark one, its minimum interference pattern is suppressed by its maximum interference pattern. Hence, the interference pattern due to S and S dash will be out of step. Now, the path difference, that is the path difference S dash S2 minus S dash S1 here also S1 is equal to, let that angle be the theta, that point be K. So tan of theta is equal to P by S, that by that, sorry, sin of theta is equal to P by S. Since the angle is very small, we take sin theta is nearly equal to theta, therefore that phase difference value Ks2 is equal to theta into d, theta into d. Also theta, that angle theta is equal to let me divide the slit into two categories. That portion is d1, that portion is d2, and d1 is equal to d2. Here the angle theta, here also the angle theta. So theta is equal to, again in the triangle we take tan of this angle, tan theta is equal to d by 2 divided by d2. In that angle, here the angle is theta, here is d by 2, here is d2. So tan of theta is equal to d by 2 divided by d2. Again that is also equal to that length L, d2 is equal to d1. Therefore d is equal to d1 plus d2. In place of d1 we write that is L by theta, L by theta, plus in place of d2 that is d by 2 theta, taking 1 by theta as common, that is L plus d by 2. Therefore theta is equal to 1 by d L plus d by 2. Now putting this value in case of that path difference concept. So path difference S1 S dash S2 minus S dash S1 is equal to d divided by the value of theta, that is d L plus d by 2, which is equal to LD divided by d plus d square divided by 2d. Since d is small, so d square by 2 is neglected, the term is neglected. We have S dash S2 minus S dash S1 is equal to LD divided by D, as D square by 2D is neglected as D is small. Now that is Ks2, which is L d by D. So the path difference is equal to lambda by 2. So LD by D, or L is equal to lambda D by 2D. If that length is L is equal to lambda D by 2D, then interference pattern would disappear. Interference pattern would disappear. Hence, the linear dimension of extended source exceeds lambda D by 2D. There will be no interference pattern on that of screen. Again, if we take theta be the angle subtended by the extended source S dash at O, then theta will be L divided by capital D. Theta is equal to L divided by capital D, which is equal to 1 by D. Put the value here, the value of L as lambda D by 2D. dd cancel out, we have lambda by 2D, or small d is equal to lambda by 2 theta, which gives the lateral distance, which is the beam may assume to be spatially coherence. Thus, if d is less than lambda by 2 theta, we get clear interference pattern. Clear interference pattern. Here we get spatially coherence. Spatially coherence. Here we get clear interference pattern. In this way, we understand how spatially coherence in case of extended source, taking Young's double-slit experiment into our account, at the spatially coherence condition, and that the clear interference pattern is observed. Here no interference pattern is observed. So, with the help of this video lecture, we understand coherence is type as temporal coherence. Its example coherence length, various types of mathematical form of coherence length. Another type of coherence, that is spatial coherence. Example for point source, the condition for spatial coherence for extended source, taking Young's double-slit experiment into consideration, we get the condition where spatially coherence observed and the condition for interference pattern. So, with this useful and informative notes, let me wind up this session. Thank you.